All right. So in class on Wednesday, we talked about each of these different inner colligative properties. So we talked about vapor pressure on Monday, and then freezing point depression, boiling point elevation, and osmotic pressure on Wednesday. And although I had a couple examples that unfortunately deviated from this, we were focusing on cases where whatever solute we were dealing with that induced these types of colligative properties was one of these non-electrolytes that when you add them to solution, what you end up with is the same number of particles of the solid thing is the same number of particles you get in solution. And the reason that we focused on these initially is that we might remember that whenever we brought up colligative properties, we said that these are properties of your solvent slash solution that depend solely on the number of particles dissolved in solution. So we focused on cases where that number of particles that go into solution is exactly the same as the number that we start with when we're in the solid phase. But we said we can also have electrolytes, which are these. So we focused on, so we can just say we focused on non-electrolytes. And largely these non-electrolytes were also non-volatile, meaning that they just stay in solution when the solvent might be going into the gas phase. But we can also have our electrolytes, and those are our molecules that when they dissolve in water, they go into separate parts. And we treat each of those separate parts as a new particle. And so we treat these different than other molecules. And so we had our example of sodium chloride where we said if you put 4 sodium chlorides into solution, you end up with 4 sodiums and 4 chlorides. And so you have twice the number of particles in solution as you did before you dissolved them in there. And we're going to see that the way we address these electrolytes, which most electrolytes are either going to be, so I can just say, like electrolytes. Most of the electrolytes we focus on are either going to be ionic salts, or just, ionic compounds, and acids slash bases. So things that when they dissolve in solution, they produce, one or, well, more than one particle. So the term we use to describe, the term we use to account for this additional particle formation is known as the Van Hoff factor. And it accounts for any and all electrolyte dissolution. Rather, we're talking about strong electrolytes or weak electrolytes. So this counts for strong and weak electrolytes. And so the way that the Van Hoff factor is defined is it's just this term, this constant, that describes how many particles you have in solution. And what happens is, in an ideal case, something like sodium chloride, when it dissolves in solution, should have, around 2 particles, 1 sodium and 1 chlorine. So ideally, the Van Hoff factor describes, so let me just spell this right, describes number of particles in solution. And we're going to see that often we're not going to approach that theoretical maximum number of particles in solution. That only happens at infinite dilution. And the reason for this is that when you dissolve something like sodium chloride, for the most part, it breaks up into separate sodiums and chlorines. And you have waters surrounding each of those. But, depending on the solution and the concentration of the salt, you might end up with cases where you still have a little bit of sodium chloride that stays together. And what we'll see is that the 2 factors that will lead to this, I think we call it an ionic sphere. The 2 factors that lead to this is that at higher solute concentration, we're going to see more ion pairing, just because at that high concentration, we just have a higher probability of your 2 ions kind of staying close to each other. The other factor that will lead to a lowering of your Van Hoff factor away from the ideal is that if you have high charge of these ions, they're much more likely to stay attracted to each other as a form like this rather than that separated state. And so here we have this table that shows a couple different solutes, non-electrolytes, which we don't really have a Van Hoff factor for because they stay as one particle, and then some particles that are electrolytes, so something like sodium chloride, which separates into sodium and chloride, magnesium sulfate, which separates into Mg2 plus and SO4 2 minus, potassium sulfate, which separates into 2K plus SO4 2 minus, and then iron 3 chloride, which separates into iron 3 plus 3 chlorines. And you can see that if we count up our number of particles, sodium chloride should give us 2, magnesium sulfate should give us 2, potassium sulfate should give us 3, and iron 3 chloride should give us 4. But because of either the relative charge of ions, so if you look at the difference between sodium chloride and magnesium sulfate, we went from +1 -1 to +2 -2. We see this larger deviation. And, we also have, in the case of potassium sulfate and iron 3 chloride, at least one ion has a larger charge than, 1 plus. But, you could see in all of these cases that we always have some slight deviation from our expected Van Hoff factor to an actual measured / realistic Van Hoff factor. And the way that we're going to employ these Van Hoff factors is with each of our colligative properties, is that we're just going to account for them. And so when we look at something like freezing point depression, which in the case of a non-electrolyte looks something like this, we have the molality multiplied by our constant for freezing point depression. We're just going to add a little factor into here, that Van Hoff factor I. So I can just say that I is equal to our Van Hoff factor, which just says that if I calculate the molality for something like sodium chloride, just like we did on the quiz as well as a problem earlier in the lecture on Wednesday, if I find that the molality of this is 0.9 molal, I just want to account for the fact that although I have 0.9 molal sodium chloride, that sodium chloride turns into, in the ideal sense, 2 particles. And so to account for those 2 particles, I'm just going to have this I be equal to something like 2. So then, even though the molality of the salt is 0.9 molal, the actual concentration of particles is something closer to 1.8 molal. So this is our concentration of sodium chloride, whereas this is our concentration of particles. And you make that same adjustment for boiling point elevation, as well as osmotic pressure. Just saying that I take any concentration unit, so whatever concentration unit you have, you just multiply that by the expected number of ions / particles produced. That's all the Van Hoff factor is doing. It's just allowing you to take your old concentration unit and then just multiply it by some factor that accounts for the fact that you have that solute turning into multiple different particles. For vapor pressure, this looks a little bit more interesting, where when you calculate the mole fraction for anything, let's say we're calculating a mole fraction for solvent, you're going to have, as normal, the number of moles of solvent in the numerator, and then in the denominator you have moles of solvent plus the moles of solute times this Van Hoff factor. Just saying that, if you want to be realistic here, what you're looking at when you look at this mole fraction of solute is you have mole fraction of solvent. You have moles of solvent divided by moles of solvent plus moles of, ion 1 plus moles of ion 2. Or, however many different ions you have. So if you have, something like iron 3 chloride, you're going to have, moles of Fe3 plus, and then 3 times the number of moles of chlorine. So you just have to account for the fact that you have all these different particles, and that's going to affect the vapor pressure just because of how we talked about vapor pressure. It's all about the number of particles at the surface of the solution. So if you have, you go from having, the number of particles equal to the molality to now 4 times as many. And so because of that multiplication by 4, you just have a lower mole fraction because you have lower moles, because now you have many moles of the dissociated thing, and that'll affect things like vapor pressure. And so the way that you might employ this Van Hoff factor within colligative properties is you're going to start the problem in a very normal way, writing down everything you know. If we're doing this freezing point depression, we know that the formula for that, I unfortunately dragged my thing over it, I think. Yeah, so let me just move this back up. I want to move it up a little bit more. Okay. All right. I don't even know what's going on anymore. Okay. As long as we moved it, we know what we need to do here. And so you're just going to write down that we know that our change in freezing point is just going to be equal to Van Hoff factor that we got from above times molality times our freezing point depression constant. And we're told that we have an aqueous solution of calcium chloride, so we know its molality is equal to 0.050 molal, and we have that that's calcium chloride. We have that its freezing point, and we're assuming this is in water, is negative 0.27, so we know that the change in freezing point is just 0 minus negative 0.27, so that's 0.27 degrees Celsius. And we know that if this is water, that our Kf, as we state right here, is 1.86 degrees Celsius per mole. And so what we're asked is, what is the Van Hoff factor for calcium chloride at this concentration? And so what we're solving for is this right here. And if we want to, we can actually solve this symbolically first before plugging in any values. We can, if we're isolating for I, we just divide both sides by molal times Kf, divide by molal times Kf, and we'd see that I is just equal to the freezing point depression, or the change in freezing point, divided by molality times Kf. And if we write that out, we get that that's 0.27 divided by 0.050 multiplied by 1.86, and we'd see that this I value is 2.9. And what we can say is that, we have this I value of 2.9, and if we think about calcium chloride, what happens when that goes into solution is we expect it to produce a calcium 2 plus 2 Cl minus. So in the ideal case, this is 3 ions or 3 particles, and so we're pretty darn close to this. So we can just say we're close to the ideal. And so the last thing I'll say about this Van Hoff factor is that we've talked about so far 2 conditions with this Van Hoff factor, where it's equal to 1 and we don't really consider it within any of our colligative property calculations, and we have that for our non-electrolytes. And what that means in terms of multiplicity is that you have, for every mole of molecule you add, you get 1 mole of particle. And so it's this 1-to-1 ratio, or you have a mole for every mole. Now we've talked about the case where the Van Hoff factor is greater than 1, and this is for our electrolytes, which they dissociate when they hit solution. And so in terms of multiplicity, or the relative number of particles versus the number of initial substance you started with, we have greater than 1 mole particle for every mole of molecule you've added. So I'd say that's greater than 1-to-1. And finally, a third way to state this is that you just have more particles or ions in solution than added in terms of the number of molecules that you've added. So that's what we talked about so far. There's one final case, which we won't really get into too much, and that's where you have a Van Hoff factor actually less than 1. And what this means is that rather than you have a dissociation of particles when they hit the solution, they're associating with each other, and they're kind of tacking together. And we'll see that this typically occurs when you have nonpolar solvents with polar molecules. And so these nonpolar solvents include things like benzene, hexanes, etc. And what's happening here is that in terms of multiplicity, we actually end up with fewer than 1 particle in solution per molecule added. And so if you had a Van Hoff factor of 0.25, that means that you have 4 molecules associate together to make 1 particle. And that's 4 molecules that you had added, and when they're in solution, they just look like 1 total particle. And what that looks like is, let's imagine that we have something like this. So this is benzoic acid. And when you add it to solution, what can happen is the benzoic acid can hydrogen bond with itself. And so, I'm putting in red the oxygen atoms that exist. So we have an oxygen atom here, which can donate electron density. So oxygen atom here, donating electron density to hydrogen here. And we have hydrogen here and oxygen atom here that are donating electron density. And what this looks like to the solution in terms of particles is this counts as one particle. Excuse me. And so with that one particle, we'll see less of a manifestation of any changes to the physical properties. And so, like I mentioned, these Van Hoff factors that are lower than 1 typically happens in nonpolar solvents. And we'll see that often it's going to be strong acids and salts that typically form ions. When they're in water, they end up being solvated, but when they're in a nonpolar solvent, they're not stabilized, and you end up with these awkward interactions, kind of like what we talked about with our initial first lecture, where we said it's not that favorable to have a dipole or a charge interacting with a dispersion force. That's like a quote unquote awkward interaction. It's one of our lowest energy interactions. And so what you'd prefer to do is just have a dipole interact with itself. So instead of doing this that we're showing here, we'd rather just have a charge interact with itself, kind of. And I'll actually orient this downwards. Carbon, CH3. And so it would prefer to interact with itself here. And so I'll kind of highlight that not in yellow, but in green. So this is our preferred interaction right here. And this is our, I'm going to grab pink, this is our unpreferred interaction right here. And so it'll maximize these types of interactions. And because of that, it'll look like fewer than one particle. And so it's all about this fact that you're not dissociating, so you don't see any dispersion, or relative dispersion of your molecules throughout solution. So we don't dissociate, so we have less dispersion of molecules, and you can maximize, in this case, when I say so you can dispersion, this means that you can maximize LDFs of solvent with itself. So, like I said, this is something that we won't get too far into, but the big takeaway here is that if you have things where if you have a solute that is kind of incongruous with the solvent, so if you have one where you're not very soluble, what happens is when you add things into solution, if you do have any slight solubility, what's going to happen is those molecules that are in solution, whether quote unquote soluble, are just going to interact with each other and allow the solvent to interact with itself. And as they interact with each other, they'll do this basically grouping up that make them look like they have less than one particle. And this is all due to a phenomenon called association, where those particles are coming together. So this association is just particles coming together. But as I mentioned before, what we're going to end up focusing on with respect to this Van Hoff factor are just those solutes that are just going to have that higher than 1 Van Hoff factor that we can account for when we look at colligative properties. So examples like this one right here with calcium chloride. And you'll see in your homework, you have, I think, 2 questions that deal with this Van Hoff factor, where the big takeaway is that you're just going to multiply whatever molality of the salt you have by either the ideal Van Hoff factor of how many ions it turns into, or an actual Van Hoff factor for the situation and concentration you have. And so if you have any questions, please feel free to shoot me an email, but that will conclude all of our discussion of Chapter 13 and should prepare you well for the exam that you have this Wednesday.